Two containers A and B containing the helium gas are prepared at room temperature with volume V and 1/3 of V, respectively. The pressure in A is 2P while the pressure in B is P. Find the pressure in A after the gas in B is added to it. Assumes the helium gas is an ideal gas and the temperature is unchanged. This question has been discussed in another videos. We use the equation of state PV equal to nRT to solve these questions. But now we are going to solve the same questions by using another methods that relies on these equations, which is the total translational kinetic energies of the gas, which is equal to 3/2 PT. Sorry, PV. P is the pressure, V is the volume. So the gas helium is the monoatomic gas. That's why we have a 3/2 here. These equations for the total translational kinetic energy for the monoatomic gas is derived very easily from this formula, which is the average translational kinetic energy for monoatomic gas, which is 3/2 kT. So please note that these symbols for the EK bar and this EKs, it carries the different meanings. With the bar, it means that it is the average translational kinetic energy per molecule for every molecule. This one is the total translational kinetic energy for the gas. By multiplying these equations with the n at both sides, then we will have the total translational kinetic energy of the gas. So the right hand side will get 3/2 nkt. The capital N is the number of the molecule. So at the right hand side nkt, now we can substitute by PV. From the ideal gas law, we know that PV equal to nkt. And at the left, the total number of molecule multiplied with the average translational kinetic energy, we will get the total kinetic energy, translational kinetic energy. So it is equal to 3/2 PV. This is how we obtain this formula. And now we are going to use this formula to solve these problems. Based on this formula, now we can write down that the total translational kinetic energy for the helium gas in the container A is equal to 3/2 times 2P times V, because the pressure in the container A is given as 2P. So we have in the bracket here, we have the 2P, and the volume is V. This is the total translational kinetic energy of the helium gas in the container A based on this formula. We can now write down the similar equations for the gas in the container B. Since this pressure in the B is P, so we have a P here, and the volume is 1/3 of the V. So we have this V in the general form changed to V/3 in this specific form for this gas in the container B. So we have 3/2 P times V/3. This is the total translational kinetic energy of the gas in the container B. After the gas in the B is added to the container A, then the container A will have the new pressure, which is P prime. Initially in the container A, the pressure is 2P. Now it changed to P prime. We want to find out what is the P prime. But the volumes for this container A is the same. So this is V here, and here also we have the V. At the left hand side, the EK, the subscript we put as AB, means that now the A and B is already added together and in the container A. Okay, so this is symbols for the total translational kinetic energy in the container A after the gas in the B is added to it. So it is equal to 3 over 2 P prime V. We want to find out what is a V prime. The total kinetic energy, translation kinetic energy in the container A, these terms, should be equal to the summations of the total translational kinetic energy in the container A plus the total translational kinetic energy in the container B. So that means the gas in the B after added to the A, the summations of the total kinetic energy in both container will be equal to the new total kinetic energy, translational kinetic energy in the container A. Now we substitute these three terms at the right hand side of these three equations into these equations. Then we have 3 over 2 times 2 PV for the first term, and 3 over 2 P times V over 3 for the second terms, and 3 over 2 P prime V for the terms at the right hand side of the equality sign. We can simplify these equations by cancel out the V, V, and the V. Therefore, in the first terms, we will have the 3P. Second terms, it is 1 over 2P. And the right hand side, we have 3 over 2P prime. So now we obtain the new pressure in the container A is a P prime, which is equal to 7 over 3P. Initially, the container's P, the pressure is 2P. Now increase to 7 over 3P after the gas from the container B is added to the container A. Okay, so this is a new pressure, and this answer is the same as the one that we obtained in the other videos, that we use the PV equal nRT, the ideal gas law, to solve two difference method. We use a two difference method to solve. The final answer is the same, which is P prime equal to 7 over 3P. Now we try to interpret what is the meanings of the result that we obtained from the calculations. It is mentioned in the questions that the temperature is unchanged. Delta T is equal to 0. So this implies that the average translational kinetic energy of the gas in the container A and the B are the same. And after the B is added to the A, the average translational kinetic energy of the gas remain the same. So these three quantities are the same. But in terms of the total translational kinetic energy in the container A, they are not remain the same, because the new total translational kinetic energy in the container A now is equal to the summations of the total kinetic energy in container A plus the total translational kinetic energy in the B. Okay, so average quantity remain the same because there is no change in the temperature, but the total kinetic energy now in the container A now is increased because we have to add up these two terms. But we know that the pressures in the container A after the gas in B is added, the pressure is increased. So what is the meanings? After added the gas B in the A, temperature remain the same, pressure increase. So this pressure increase is due to what reasons? Why the pressure of the gas increase? We know that if the delta T, if the temperature is not changing, so the average velocity for this gas in the container A will remain the same. So if the average remain the same, how come the pressure in the container A increase? So what is the reasons to make this pressure increase if the temperature is remain the same? The answer, we can get it from these two equations. At the left, it is the P equal to 1/3 rho mean square speed, or it is equal to 1/3 of rho RMS speed square, where the P is the pressure, rho is the density. And also we know that the average translational kinetic energy half m mean square speed is equal to 3 over 2 kT, which is depends on the temperature T. So in terms of VRMS, we can write in this form. Now we change the mean square speed to the VRMS square. So if the temperature change is 0, so that means this T is constant. If T is constant, means that this VRMS square is also the constant. Okay, M wouldn't change because we consider the same types of the gas. So that means before and after the gas in the B is added to the A, the average translational kinetic energy remain the same. Due to this equation, we can know. Because when the T no change, then the terms at the left hand side, the quantity at the left hand side also won't change. So if this one, average translational kinetic energy is not changing, therefore this VRMS square also won't change. So if this one won't change, so that means in these equations, the pressure, the change of the pressure, we know that pressure increase is not due to this VRMS square. It is due to the rho, which is the density of the gas in the container A now is increased. So due to the density in the container A increase, it causes the pressure in the container A increase without affecting the temperature. Okay, so after the calculations, we hope that all of you can see these pictures. Not only obtaining the answer only, we must try to interpret and what is the meanings of the result of calculations and able to see the pictures behind the calculation. We should able to see the pictures that reflects what happens in the system that we are investigating. Okay.